I'm Steve Harding. I'm a Professor of Physical Biochemistry here at the University of Nottingham, and one of my main interests is in the properties of large carbohydrate polymers, of which chitin and chitosan is an important class.
Chitin is an essential substance of the shells of lobsters and their crustacean relatives. It's also found in the exoskeletons of insects and spiders, and it's the molecule that gives fungi their shape. It's tough and durable, and is laid down in a crisscross pattern to produce a sort of waterproof ply. It's the British Midlands that are the epicentre for lobster surprise number 4. Chitin could well be a wonder molecule for us all, if we can understand and apply its properties. Steve Harding.
We're at the University of Nottingham at the National Hydrodynamics Centre, and the noise in the background is an ultracentrifuge, and we're just preparing to do a run on a chitosan solution.
Chitosan is a solution of chitin.
That's right.
A naturally occurring substance, but what is it and where does it come from?
Right, chitin comes from the shells of crabs, lobsters, other crustaceans, and it's an insoluble material which forms the exoskeleton of these creatures.
Do we know enough about chitin in nature, Stephen, to know what it actually does to the animal from which it came, in the shell of the lobster or the crab or the prawn?
Yes, I mean the chitin forms this network which is impermeable, so water can't get through, nor water get out, and of course with it being a very strong material, it protects the crab, the lobster or whatever from damage, to limited extent of course, but it's quite an effective protective layer for the animal.
It seems a very strange leap to make. Here we have a material in nature which adds to the impermeability of crustaceans' shells, but you are making it soluble for it to do something else. Why? I have to ask why.
Well, the reason is that when we do this, we produce a polymeric molecule which is quite unusual. This chitosan molecule is a polymeric, positively charged molecule. Now, polymers in nature tend to be either neutral, that is, have no charge, or negatively charged. Now, if we're producing from natural sources this polymeric, positively charged molecule, then it's going to stick.
Its positive charge means the long chitin molecule is sticky to anything that has an opposite charge, rather like opposing poles of a magnet that attract each other. In life, most roaming particles have a negative charge, so this gives chitin valuable properties. George Roberts works with Nottingham University on the applications of crustacean chitin. He told me it already has uses, mopping up polluting substances in water and excess dye in the textile industry. It's a sort of hungry molecule then. It will mop up things for you.
It mops up metal ends and a certain number of dye classes very, very well indeed. Very, very high absorbance rates.
I saw the dreadful term fat buster in some of my research notes. I understand its potential for fat busting is being looked at.
Yes, there have been in vitro studies on it, and it does bind to lipids quite strongly.
Now, lipids are the fat that's normally floating around in our body.
Yeah. And since chitosan itself is not normally metabolized in the human body, it means that this will be eliminated, the chitosan together with the lipids. That's the theory.
If it's capable of mopping up these things, it's a hungry molecule, would it have applications in antibacterial uses?
The big application that's likely to develop is in the biomedical field, because it has a lot of very important properties. It accelerates wound healing and reduces scar tissue on the healed wound. Chitosan itself is a bacteriostat, so it immobilizes bacteria on its surface, but it doesn't actually kill them. We have developed a derivative of chitosan which is a very active contact biocide, active against a number of organisms. One of the interesting ones is MRSA, and we're currently working to try and incorporate it into wet wipes for wiping down hospital beds and so on to prevent the spread of MRSA. And we also have a wound dressing company that is doing clinical trials on an advanced wound dressing that includes this chitosan derivative. And in cosmetics, particularly derivatives that are water soluble have been used. They have very good moisture retaining properties, and they've been used in salves and skin creams, and also in shampoos and other hair products because of their film forming properties in that case.
Makes the hair shine.
Yes, and also they have a test which can tell you how easy it is to comb the hair afterwards, and the film that you get is very good. It scores very highly on that.
So many of our Radio 4 listeners could now be walking around with extract of crab on their head.
Yes, or prawn or what have you, yes.
Chitosan doesn't smell, of course.
Sometimes, again, it depends how pure it is. It does have a bit of a smell. The other problem is one of the common solvents used is dilute acetic acid, which smells like vinegar. And you've got to be very careful that you get rid of it all. Otherwise, you do have an odour.
Hair smelling of fish and chips.
Yes, not a very pleasant idea.
Anything else? Any surprising things it might be used for?
Well, it's very good as a flocculating agent, and something like 400 or 500 tons are produced in Japan for treatment of wastewater.
Now, flocculating agents are things that make particulate material in a solution form clumps and fall to the bottom.
That's right. And it's very good at doing that, again because of its positive charge, its cationic nature.